Chapter 7 Sand 7.1 Longitudinal Waves. Let's begin. Observing a longitudinal wave. The corner of this book shows a flipbook animation. While the wave travels horizontally, the particles also vibrate horizontally, so it shows the propagation of a longitudinal wave. You have learned on page 5 that longitudinal wave is a series of compressions and rarefactions. And what's more, 1. Particle vibrations and wave motion. For a longitudinal wave, the direction of vibration of particles is parallel to the direction of propagation. We may use a slinky spring or use a longitudinal wave model to show the motions of particles. Let's take a look of the following demonstration.
Set up a longitudinal wave model on an overhead projector. Switch on the model so that a longitudinal wave is projected on the screen. Observe the wave pattern and the motion of one particular line in the pattern.
As computer simulations are handy, teachers nowadays do not use longitudinal wave model anymore. You can see from the following simulation, when a longitudinal wave travels, which is a series of compressions and rarefactions, the particles are set into vibrations along the direction of propagation, with the same period and frequency of the wave. All particles vibrate similarly, but different in their phases of motion. Example 1. Particle vibration and wave motion. Refer to page 163. The wave repeats itself in 8 seconds. This is the period of the wave motion and also the period of the particle vibration. The frequency is given by 1/8 Hz. The amplitude of vibration of particle B, which is gray in color, should be the displacement at t equals 1 second, which is 0.8 cm. Lastly, we may focus on the motion of the compression to determine the wave speed, which is 11 minus 3 divided by 8 equals 1 cm per second. To measure the wavelength, we may measure the separation between successive centers of compressions, or between two successive centers of rarefactions. On the other hand, the separation between two successive particles with zero displacement is half the wavelength. Why? For particles separated by one wavelength, they are vibrating in phase. For particles whose equilibrium positions are separated by half a wavelength, they are vibrating exactly out of phase. Note that these particles are not separated by half a wavelength between them, but only their equilibrium positions are separated by half a wavelength. You may refer to the supplementary information at the bottom of the page for details. Example 2. Vibrations on a longitudinal wave. The figure shows a snapshot of a longitudinal wave. There's no hint about the direction of propagation. However, we can still tell the direction of particle vibration. The wavelength of the wave and even the wave speed by V equals F lambda if frequency F is given. Not that difficult indeed. Do check point 1 below.